In this section, we're looking at partial derivatives. Okay, so our first example, oh, I'm on the wrong screen. Let me get up. There we go. Our first example says we need to find it wants the partial derivatives. Okay, oh, hold on. Let me switch my colors. Okay, it wants dz dx, and if you keep reading, and those are Greek deltas. If you want to keep reading, then you'll see that that's the way that you see the notation a lot of times. Okay. Um, well, I know if it was an F right there, we'll just pretend like that's what it says. But it's saying I want the partial derivative with respect to x. So it means look at all of these terms, and we've got 3. Okay. And what you're doing is taking the derivative with respect to x. Okay. So if I took the derivative of 3x, it's 3. Okay. When I get to this term, all right, you kind of want to ignore the y squared and say, all right, I need to take the derivative of negative x squared, so it would be a negative 2x. The y squared is treated as a constant, and it just comes along with your problem, okay? You just kind of ignore the y's. And then when I get here, again, I'm taking the derivative of the x, so I'm going to take the derivative of 2x cubed, and I would get 6x squared, and you bring the y along, okay? And then if we did the partial derivative with respect to y, again, I usually call them like that. Okay, then we start back over, and I take the derivative of my 3 terms, but now I take it with respect to y. So if I look at that first term, 3x, do you even see a y in there? No, so that's like taking the derivative of a constant. That one's going to go away. There is no y in there, so the derivative of it is 0. So then I go to my next one, okay, and remember you're kind of ignoring the x squared. You're saying I've got a negative y squared. So my derivative here would be, it's kind of like you're ignoring the x squared, and you take the derivative of y squared and get 2y. We don't want to write it like that. We would put the negative 2 out front and then say it's x squared y, okay? And then the same thing when you get here, okay, you're just kind of ignoring the 2x cubed. Oh, let's write it up here. You're kind of ignoring that 2x cubed and saying, hey, the derivative of y is 1. And so we can just call that 2x cubed. So if you want to write it in 2 separate steps, you can. But here are both your partial derivatives with respect to x and then with respect to y. Okay, let's keep going. Alright, so same thing, I want the partial derivative with respect to x and then the partial derivative with respect to y. So let's take it with respect to x first. So the derivative of 2x squared is just 4x. And here, okay, again, I'm going to take the derivative of the x part, which is negative 8x, and then I bring the y along. And then when I get to the end, as in our previous example, I want to take the derivative of y to the 4th with respect to x. If I don't have an x in there, then it's treated as a constant, and the derivative is 0. Okay, so let's go back now and get it with respect to y. So no y's in there, so the derivative of that is 0. Okay, here I'm just going to kind of ignore that x squared and say I've got negative 4y cubed. So the derivative of that would be a negative 12, and it's y squared. And I'm going to leave that x squared that's in the middle of it alone, because, you know, we write our variables in alphabetical order. And then the derivative of y to the 4th is 4y cubed. Alright, so now I'm going to do the same thing, find fx and fy, and then I'm going to evaluate it at that point. So let's take the derivative with respect to x. So again, I'm just looking at that x squared and saying our derivative is 2x and bringing that y cubed along. So now if I evaluated that 1, 2, I'm plugging in a 1 for x and a 2 for y. So that's 2 times 1 times 8, or 16. And then if I took the derivative with respect to y now, then I'm taking the derivative of y cubed and getting 3y squared. But I'm going to keep that x squared in the middle of it. And now again, plugging in 1 for x and 2 for y. So that's 3 times 1 times 4, or 12. Alright, these next examples are just a series where we find the derivative with respect to x and the derivative with respect to y. Alright, so let's find fx. Alright, now one of these derivatives is going to be a lot easier than the other one. Because I have an x on the front, I have to do a product rule. Okay, so I'm calling 1 x, and I'm calling 2 e to the x squared y. So if I did d1, the derivative of x is just 1, and d2, well, that would be copy down your problem exactly. We did this at the beginning of the semester, times the derivative of the exponent. Now, derivative of the exponent with respect to x would be 2x, and then have that y. So d2 is really going to be 2xy e to the x squared y. Okay, so if I filled in fx, I have to use a product rule. It's 1 d2 plus 2 d1. So if we plugged it in, 1 is x, d2 is 2xy e to the x squared y, plus 2, which is e to the x squared y, d1, which is 1. And if I cleaned it up a little bit better, I get 2x squared y e to the x squared y plus e to the x squared y. And if you wanted to, you could factor out that e to the x squared y and get 2x squared y plus 1. Okay, so either one of these answers are acceptable with me. And now if I did fy is the easier one, okay? Because there's no y on the front, that x is treated as a constant. I don't have to do a product rule. I just take the derivative like normal. You copy down your problem, and you multiply by the derivative of the exponent. Okay, well, the derivative of the exponent with respect to y would just be x squared, because the derivative of y is 1. So this one is a little bit easier, because if I multiply those x's, I get x cubed e to the x squared y. Okay. Alright, so we'll go ahead and write that as x squared plus y squared to the 1/2. Alright, so for fx and fy, we got to use a chain rule. So it would be 1/2 times the exact same parentheses, but subtract 1 from it. When you subtract 1, you get the negative half. Alright, times the derivative of the inside. So the derivative of x squared is 2x, and then the derivative of y squared with respect to x, though, is just 0. So the only thing I have is that. So what happens with the 1/2 and the 2 is that they cancel. I've got an x on top, and then I'm going to drop that to the bottom. Fy is going to look very, very similar because I still have to do a chain rule. 1/2, the exact same parentheses, drop it by 1. Alright, now this time when I do the derivative of the inside, the derivative of x squared is going away because there's no y, and the derivative of y squared is 2y. And again, the 2 and the 1/2 cancel, so I'm left with a y on top and the square root of x squared plus y squared. Alright, so let's see what's next. Okay, so now I have x over x and y over y, so this is going to be your quotient rule. Okay, so let's do fx. Alright, it would be low d high. Alright, the derivative of the top with respect to x is just y minus high d low. Alright, the derivative of the bottom with respect to x is just 2x over the low squared. So if I distributed that y, I get x squared y plus y cubed minus, if I multiply that, I get 2x squared y over x squared plus y squared squared. And look on the top, you've got some like terms. You can combine those up and get y cubed minus 1 x squared y over x squared plus y squared squared. Alright, and fy is going to be very, very similar. I've got low d high, well, the derivative of the top with respect to y is x minus high d low, the derivative of the bottom with respect to y is 2y over the low squared. So if I distribute the x, now I get x cubed plus xy squared minus 2xy squared, and I've got those like terms on top again. And so I've got x cubed minus xy squared over x squared plus y squared. All right. Natural log. So let's remember natural log derivatives. Remember we drew a fraction bar. Whatever was behind the ln went on the bottom, and the derivative of the bottom went on top. Well, the derivative of the bottom with respect to x is just 2x. And there's nothing I can do to reduce it. Same thing with the y. Whatever's behind the ln on the bottom, and the derivative of that on top, which would be 2y. All right, now we're looking for 3 partial derivatives. I got to do f with respect to x, with respect to y, and now with respect to z. So now let's think about those. Because of this x on the front and then the x in the exponent, f with respect to x is going to be the hard one. That's going to be a product rule. The other two are going to work really, really quickly. So let's see, for the fx, I got to do a product rule. I need a 1 and a 2. Okay, and so D1 would be 1 and D2 would be exact problem times the derivative of the exponent. Alright, but remember we're taking it with respect to x. The derivative of xy is just y, and because 2z doesn't have an x in it, it just goes away. So really, if we multiply that, D2 is y, e to the xy plus 2z. Alright, so fx is going to be 1 d2 plus 2 d1. So let's plug it in. So 1 would be x, d2 is y, e to the xy plus 2z plus 2, which is e to the xy plus 2z, d1, which is 1. So it's xy, e to the xy plus 2z plus e to the xy plus 2z. And if you want to, I probably would factor out the e to the xy plus 2z, and it's xy plus 1. Other two, much, much, much faster. The derivative with respect to y is copy down your problem and multiply it by the derivative of the exponent with respect to y. Well, this one's the only one that has a y in it. The derivative of y is 1, and I bring that x along. So if I cleaned it up, it's x squared, e to the xy plus 2z when I multiply those x's. And then same thing with respect to z. I'm going to copy down my problem exactly and multiply by the derivative of the exponent. Well, there's no z in here, and then the derivative of, so that goes away, and the derivative here, 2z, is just 2. So derivative of f with respect to z is 2x e to the xy plus 2z. Okay. All right, 2 more. Now, second partial order derivatives, we have 4 of them. Okay, so I usually tell people to kind of approach it like this. First, do the first partials with respect to x and with respect to y. So if I took the first derivative with respect to x, I get 3y squared, that middle goes away, plus 10xy squared. And if I took it with respect to y, I get 6xy minus 2 plus 10x squared y. Okay, so that's going to be the first thing you do. Find your first partial with x and first partial with y. Then from this one, you're going to get 2 of them. You're going to take it again with respect to x. So if I took it again with respect to x, no x here, the derivative of that one would be 10y squared. And then you're going to go back and take it now with respect to y. So the derivative of 3y squared is 6y, plus the derivative of this one would be 20xy. Okay. Alright, so we're the same thing over here. You're going to take that one and take it first with respect to x. So if I took it with respect to x, I get 6y, that derivative of minus 2 goes away, and I get plus 20xy. Okay. And then you're going to go back to it and take it now with respect to y. So you would get derivative of 6xy is just 6x, and the derivative of negative 2 goes away, and the derivative here would be 10x squared. Okay, and if you'll notice, most of the time those two are the same. Okay, and let's do our last one. Okay, so again, I'm going to get fx first and then fy. So if I do the derivative with respect to x, I get 8xy squared plus 2. And then if I took it with y, I get 8x squared y plus 2x, derivative of that go away, plus 8y. Alright, so from here, I'm doing it again with respect to x, which would be 8y squared. And I'm going to go back to it and go now with respect to y. So that would be 16xy, and the derivative of that 2 goes away. Alright, so from here, I'm taking it once with respect to x, which would be 16x, and then the derivative of 8y would go away because you don't, so I forgot my y right there. Oh, the 8y would go away because you don't have an x in there, and then I'm going to go back and take it now with respect to y, so I'd get 8x squared plus 8. And again, notice those. Alright, so you go practice your My Math Lab homework.